Okay, so we're going to start topic 8 today in this video, which is all about friction. So the last few topics of this course are kind of delving a little deeper into topics that you've already discussed in previous courses, mainly in physics and calculus. So you've used the idea of friction in physics before, and these topics also are going to come up in different later courses that you'll take in your civil engineering curriculum. So the concept of friction, what we want to do is we want to talk about dry friction and how we can analyze the equilibrium of rigid bodies that are subject to friction force. So the difference between the friction we're going to discuss in this class versus the friction we're going to discuss in dynamics is that when we're dealing with friction in dynamics, we need to overcome that friction force in order to cause the body to move. In this class, we're not trying to overcome any friction force because we're in static equilibrium, which means our systems are not moving. So the type of friction that we're dealing with is very specific in this class. That's why this is a relatively short topic set slide. It's only 18 slides. And we're sticking to this one type of static friction, or friction where we're not moving. Static equilibrium concept, okay? So we're going to talk about dry friction, and another name for dry friction is Coulomb friction. So either of these you can use to kind of look up resources to better understand dry friction. You can see this in the book as Coulomb friction or as dry friction. And as a little kind of reminder of what we're talking about, friction is a force that basically resists motion, okay? The definition of friction is resistance to motion. Okay, so if you have two contacting surfaces that are sliding relative to each other, one is resisting motion, and that is the direction of your friction. So your friction is always in the opposite direction of motion. Okay, and it's always tangent to the surface at the point of contact, directed opposite of motion. And when we're dealing with dry friction, this occurs between the contacting surface of bodies when there's no lubricating fluid. Okay, so there's no slippery surfaces here. This is just dry friction. Okay, so dry friction theory here, this is an example here. We have a box that is on a flat surface, and we're pulling the box with some force P. The box has some weight to it, and of course it also has a normal force. So if we want to draw the full FBD of the system, this box also has a normal force going up. And the reason that normal force is super important is because our friction force is a function of our normal force. So when we're pulling on this force P, the body wants to tend to move in this direction. So we know that our friction force has to act in the motion opposing, or in the direction opposing motion. So our friction force would be in this direction, and it's actually a function of this normal force that acts perpendicular to the surface of contact there. Okay, so we have the resultant of our normal force depending on that contact surface. We have the resultant of our friction, okay, that act at some location. This is a general picture here. It can act at some location, X, okay, which is the centroid of the normal force distribution. And this friction and normal force where they act here at the centroid, this is the centroid that's necessary to balance this system and the tipping effect caused by P. Because remember, we are not moving right now. We want to stay in the static equilibrium space. So we need to figure out where that normal force and friction force need to have their resultants so that this force P does not cause the system to tip or to move. Okay, sometimes you can think about this. If the friction is so high, instead of sliding, you're actually just going to tip this. Imagine you had a box on a really rough, shaggy carpet, and the box didn't have a lot of weight to it, and you pull on the box really hard. What's going to happen is the box is actually going to tip forward before it slides on the floor sometimes, especially if that force P is really high above the ground. Like let's say you're pulling from the corner. Of course, if you pull lower to the ground, it's dependent on this height H, then you're going to experience sliding rather than tipping. So what we want to figure out for these problems is that sweet spot for the resultant of the normal force and your friction force so that we don't get tipping and we don't get sliding and we can stay in static equilibrium here. Okay. Now, we also have this idea of impending motion, which means you're not in motion yet, but you're about to move. So you might have already seen this formula Fs equals mu s times n, and mu s is called the coefficient of static friction. The reason this is the coefficient of static friction, again, is because the system has not moved yet. Okay, so again, let's think back. If this block is on a slippery surface now, then we might not have enough friction to resist motion if you're pulling with P, right? You can think of pulling a cardboard box on an ice rink, right? There's not enough friction there. You just have to pull with a really light force P, and you'll be able to move this box pretty easily. This means the block is going to start slipping, and as we increase P, then F correspondingly increases until it reaches some max value Fs, which is the last possible value of the friction force before you move, okay? It's like the maximum value of friction before it kind of gives in, can't resist anymore, and your object starts to move. Once you reach Fs, we're no longer in static equilibrium, we're unstable, because any minute increase in the force is going to cause motion, which we don't want, right? And we know that Fs is directly proportional to that normal force, like we talked about earlier, as a function of mu s times n. So mu s is a given. It depends on the material that your object is sitting on. So you'll always be given that mu s, okay? And now the next step of impending motion right before we start moving is motion. So P becomes greater than Fs. We can no longer use this formula because remember that formula is basically mu s and Fs. This is static friction. We're no longer dealing with static friction when you get to motion. We're dealing with kinetic friction. So now we have to deal with a different mu value for kinetic friction and a different force F. It's still a function of your normal force, okay? But we've basically surpassed that maximum value to where we are no longer in motion and our system has succumbed to being in motion, okay? So what we're dealing with here is an image that looks like this. The friction force can resist a lot before it gets into motion, actually more than it can resist when it starts moving into motion because it's already given in at that point. So you can resist a lot through Fs, and then once the motion starts, it drops down to Fk. So your Fk is always lower than your Fs. Your system wants to resist this motion. Once it gives in, it's accelerating, it's moving, and you're in that Fk state, which is actually a lesser force required to maintain that motion. Okay. Okay. Dry friction problems. So we have different kinds of problems. The first type of problem is no apparent impending motion. Okay. These are strictly equilibrium problems where the number of unknowns equals the number of equations of equilibrium. So these are very straightforward problems that we can do. Once we know the frictional forces from the solution, the numerical values have to be checked to make sure that we're definitely still in the static friction zone. And then if we really are still in the static friction zone, that means our analysis was okay and we can just stop there. If for whatever reason we surpass that static friction, then our analysis is invalid and we have to kind of go back to the kinetic friction and start all over. Okay. The next type is that we have impending motion. So this is basically when we're going to approach movement and we have a total number of unknowns is equal to, yes, equilibrium equations, but also our friction equations. So we have to use the Fs for impending motion, and the minute our slipping or movement starts, we'd have to switch to moving Fk. So these problems get a little bit more complex because you just add to the number of unknowns that are present in your problem. The third type is impending motion at some points of contact. Okay, this is basically when we have more unknowns than equations to solve for, and we would have to explore some different types of analyses to figure out how to solve for what's going on here. So you may have already noticed the problems that we will be dealing with and won't be dealing with in this class, and we're not going to be dealing with anything that has impending motion at some points of contact. That's for potentially future classes, if any at all. Okay, we'll have to do some higher level of analyses for this. Okay. Now, let's go ahead and try a couple of examples here. Okay, so we have a uniform crate and we're given a mass of 20 kilograms. If a force of P equals 80 is applied to the crate, determine if it remains in equilibrium, and we're given the coefficient of static friction. So I like to think of this topic as mainly a review because you've already seen these problems in physics, which is a prerequisite for this class. So this is, if you're wondering why this looks so familiar, it's because you've done these problems several times in your physics mechanics class. Okay, so we're gonna basically do it again here just to make sure that this concept is clear from the statics perspective. Okay, and we're gonna start by drawing our FBD of the system here. So I'm gonna redraw the box on the side, or the crate on the side here. And we have this P equals 80 Newton force on the side. We're being told that the system is 20 kilograms, so we have 20 G. And then we also have a normal force. And for now, I'm gonna draw the normal force off to the side over here. I don't know where it acts. I want to figure out where it's going to act. And I also, if I'm trying to move in this direction, that means my friction force is in this direction. And I'm going to draw this distance x. This is like my origin point of the centroid. I don't know where the normal force acts, so I'm going to draw it arbitrary at some distance x. And this is 30 degrees. Okay. The normal force must be some distance away from the crate center line to counter the tipping effect caused by P. That's why my normal force is not in the middle. You can think about this. Imagine you are pushing on this crate with an 80 Newton force. My normal force is shifting over to counteract this box from tipping. So that's why I have this normal force off to the side like this. This is the big difference in the problems you might have previously done. I have three unknowns here. I have F, X, and NC. And it's great because I have three equations of equilibrium. So this falls into the first category, hopefully, that we have no motion. Okay, we'll have to check that at the end, but let's start by summing forces in the X direction and setting those equal to 0 for equilibrium purposes. Going to continue summing forces in the Y. We have negative 80 sine 30 plus NC minus 196.2. And we can solve, I call it NC is 236.2. Okay, now sum of moments about 0.0 is 0. Counterclockwise is positive. We have 80 times the moment arm of 0.4 minus 80 cosine 30. And we get X equals negative 9.08 millimeters. Okay, what does that mean? That means that actually our resultant acts to the left of 0.0, not to the right where I drew it. Actually acts to the left. Really, it's here. Okay. Now, why does this result tell us that no tipping occurs? Because our normal force is less than 0.4. Okay. If our normal force is greater than 0.4, so here, our normal force, sorry, not the normal force, the location of the normal force, it's less than 0.4 meters, which means no tipping. Once the normal force acts past the centroid, to the right of the centroid, it has to counteract the tipping force. But if it's acting before the centroid, that means that the force P is not great enough to cause tipping. Okay, so now we're good with that. No tipping occurs. Let's check our max friction force to make sure everything is static. So we have F max equals mu S NC. 0.3 is our mu S that was given, times 236.2. We get 70.9 kilonewtons. And that is less, here, that's less, we get 60.3. We get, oh, what am I doing? No, this is 70.9. But our F force is 60.3. 69.3. Okay, this here, this F here, my force of friction is less than the max friction, right? It's less than F max for static friction of 70.9, so we're good. No slipping. It's close, very close, but no slipping occurs. We're still static. Okay. All right, so let's go ahead and do example 2. It is observed that when the bed of a dump truck is raised to an angle of 25 degrees, the vending machines will begin to slide off the bed. And we want to determine the static coefficient of friction between a vending machine and the surface of the truck bed. So we have here the real world scenario, and we already have an analytical diagram that's shown for us on the side here. So again, I'm going to start by drawing the FBD off to the side. Okay. And RG is right here. We have some weight. Motion is going to the, or in this direction, so we know our friction force is going in this direction. And our normal force, of course, is perpendicular to the surface, and it acts at some point X away from the centroid. And we have a 25-degree angle. All right, so let's go ahead and start here. Let's sum our forces in the X direction. What I'm actually going to do here, let's see, I'm actually going to use this direction for my X. So let me redraw. I'm going to use these axes here. Let me use a different color to show that. I'm going to use the inclined surface actually. So I'm going to say this is my X and my Y. I can think of them as X prime, Y prime. You can do either one. This just saves me from having to do the normal force and the friction force in components. And now I just have to do the W in components. So I'd have W sine 25 minus F equals 0. Sum of Fy would be like that upper direction that I showed. And I'd have normal force minus W cosine 25 equals 0. And I'm actually going to sum moments about this point here. I'm going to call this O, so I can eliminate that normal force. And I would have negative W sine 25, moment arm of 2.5, plus W cosine 25, moment arm of X. Okay. And we know that slipping occurs at this 25-degree angle because that's what's being told in the problem. It's observed that when the bed of the dump truck is raised to an angle of 25, the vending machine begins to slide off the bed. So we know that slipping starts at 25 degrees. Okay, so what we're going to do is we're going to combine this equation and this equation, and we're going to plug everything in for this. And we get W sine 25 equals mu s w cosine 25. And we have mu s is equal to tangent 25, sine divided by cosine, and we get 0.466 here. Okay. So we have a term for this theta, which is the angle where slipping starts. And we call this the angle of repose. Okay. And this is equal to the angle of static friction. Or actually, we use phi for this. Phi s. Okay. Now theta, this theta that we're using of 25, this is independent of w. Knowing theta allows us to determine mu s. Why is it independent of w? You can see here, when we set up the equation, the w actually cancels out, and the mu s is a function of just this angle. Okay. Okay. So we have our mu s is equal to 0.466 here, right? Okay. So we're going to move on now, talk about wedges, okay? And wedges are considered a simple machine because we can transform an applied force into a much larger force directed at the right angle to the applied force. So what does that mean? Basically, you can see the system here. We would have a force, an input force in this direction, and this input force would be transferred into output force that is much larger in an angle, I'm going to show you, an angle, a right angle to the force that you're applying. So you see here, these are perpendicular to each other. Okay, so we can actually take this smaller input force, make larger output forces at a different angle, just using the simple machine of wedges. Okay, we can use wedges to lift blocks, and the way that that works is actually through frictional forces. So we have our frictional forces here, F1 and F2 shown, and they have to oppose the motion of the wedge to the right. And then we also have F3, which has to oppose the motion of the wedge upward. And the location of the normal force in this case aren't important because the block and the wedge don't tip. So we're only interested in the location of the normal force when we're dealing with tipping. Here we're not dealing with tipping, we're dealing with actual motion to the left, right, or upward. Okay, so let's do an example here where we're dealing with a wedge. Okay, we have a uniform stone, and we're given the mass of this stone, and it's held in the horizontal position using this wedge at point B. Okay, so it's kind of propping it up to match what's going on at point A here. Okay, if the coefficient of static friction is mu s equals 0.3 at the surface of contact, determine the minimum force P needed to remove the wedge, so to basically pull that wedge out of there, and assume that the stone does not slip at point A. So they're giving us that information ahead of time. So what we want to do here is we want to break this system up, and we want to draw the FBD of first the stone and then actually the wedge, so we can see this interaction and what's happening here. So this is our stone. And we were given that the stone has a mass of 500 kg. And we know that there is going to be some resistance to the motion, this friction, and some normal force. And it doesn't tip, so it's some normal force to the left of our centroid. And then we also know here that where the wedge is, right, we have this little wedge system here. Let's see if we can draw what's happening. Little wedge system. We also have this normal force of that at point B where the wedge is. So normal force at point B, but then we also have this resistance here of 0.3 NB. So mu NB, this is just the frictional force. And we know that this is at 7 degrees. Okay. Now if we want to draw the FBD of the wedge to see what's happening with the wedge, we're going to, again, draw equal and opposite now, 0.3 NB. If the system is going to be moving in this direction here, if the wedge has a frictional resistance in this direction, then it's equal and opposite on the web. Because remember, this is FBD of the stone. So we're drawing, let me write this a little better, 0.3 NB. On the wedge is moving in this direction. So the friction has to be resisting in the other direction. And it's equal and opposite to the other system. And then, of course, this normal force for the wedge is from the block in that direction. But then we also have that contact surface C at the bottom for the wedge, right? Which means we also have another resistance to motion in that direction. And of course, we also have this force P pulling on the system trying to move the wedge. So our impending motion is this direction for the wedge. Okay. And we want to know the minimum P required for F equals mu Sn at surfaces of the contact with the wedge. Okay, and we know that at A, we know that the stone at A has to be less than or equal to mu Sna because we're told no slipping. We know that this has to be less because we're told no slipping. Okay, so let's start with the FBD of the stone. Let's start with this FBD of the stone that we're working with. Let's sum our moments about point A, set that equal to 0, counterclockwise is positive. We have negative 500 G times a moment arm of 0.5 plus NB cosine 7, 0.3 NB and we can actually directly solve for NB. And now we can look at the FBD of the wedge. I'm plugging in the 2383.1 sine 7, and I can solve for NC. And then my last equation here. And I can solve for P as 1.15 newtons. Okay. So P is positive, so the wedge must be pulled out. Okay, since P is positive, okay, if P was 0, then the wedge remains in place, right? This is self-locking. Okay, And the frictional forces B and C would satisfy basically FB is less than mu SNB and FC is less than mu SNC. That's only if it were 0. But since it's positive, then the wedge has to be pulled out. Okay, so that is our final answer. And this is the last example of this topic slide.